Welcome back, everybody, to this new video, the last one on part one of graph sketching. So the lecture today will actually be on a relatively confined subject called global minima maxima. Global is sometimes referred to as absolute. We're going to use one term or the other. They're interchangeable. So let me show you a little bit on a graph what I mean by global or absolute. So suppose I have a y-axis and an x-axis. So y and x in this way. And I want to do something like this. Not a very original graph, but it'll have to do. All right, so let's give ourselves a few points here. So say this is our point A, our point B, another important point C, and another point D. So basically, the difference between absolute and relative will actually be shown here. A relative min or a relative max, you remember, this is a point actually where either the first derivative is equal to 0 or does not exist. So what's the difference between relative and global? Well, this graph actually can sort of instruct us in that matter. So on the interval AD, on the closed interval AD, so basically from here to here, there are a couple of very interesting points that we certainly recognize. For example, what is B? X equals B is what with respect to the graph of f of x? What do you think? X equals B. This is the point here, right? So B comma some unknown y value. What I know is that in the neighborhood of B, right? If I move a bit to the left or if I move a bit to the right, the graph will actually go up. What do we call such points that are kind of at the bottom of the valley like this, locally? We call them local minimum. Is a local minimum, right? Latin word meaning the lowest. One minimum, two minima. The plural of minimum is minima in Latin. So we have that. What else do we have? Look at this graph. What do you have here? We have another point that we can probably recognize as having some importance here, namely the point C. What is the point C? Well, the point C lies right there in terms of y value. So it is C comma f of C, and f of C is a local y value that is pretty high, isn't it? That is a value that if I look a bit to the left, it's lower, and if I look a little bit to the right, it's lower as well. What do we call that? A local maximum. Is a local maximum. Here we go. Okay, so that's basically stuff that are from the graph, and we are familiar with this sort of thing. Now the question I'd like to ask is this. On the interval AD, I'm still talking about the interval AD here, what is the absolutely, let's call it this way, absolutely largest value of y? So I'm going to limit myself to the interval AD, and I'm going to be looking on that interval for the highest y point. Is the highest y point occurring at A? Well, the y point at A is here. Is it at B? No. Is it at C? Uh-huh. Is it at D? No. So you can tell that when x is equal to C, it actually reaches the absolutely highest y value in the interval. So happens, this absolute value happens when x is equal to C. And I can actually ask, similarly, what is the absolutely lowest, or smallest probably is a better word, smallest value of y still on the interval AB. Okay, well, is the smallest value of y happening at A? This is the value of y happening at A. It is not the smallest. It is not here. It is certainly not here. It seems to be at the point D, right? The point D has this as its y value, and there are no lower y value in the interval. So this happens when x is equal to D. So we call x is equal to C the absolute or global, right? The absolute or global, same thing, maximum on AD. Just like we call x equals D, the smallest of all the y values, so the absolute min, the absolute, also known as global minimum, min on the interval AD. So what does absolute means? It means that if I consider the entire interval, I don't necessarily only look at the local min or the local max, I also look at the end points of the interval. And whichever has the highest y value is the absolute max, and whichever point has the lowest y value, it is the absolute min. A fairly easy concept, right? So the question in this chapter will simply be, how do we find those things, right? So it shouldn't be very complicated. So now that we have sort of explained a little bit what this is about, let's take a look at an example. Let us take a look at an example, but before, perhaps we should summarize the method, the strategy to find the global min and the global max. So strategy to find global, also known as absolute global min / max on some sort of an interval, let's just call it x1, x2 for lack of better terminology. So what are we going to do? What kind of strategy could we actually come up with? I can sort of lay it down for you in 3 steps. To find global min, global max, the first step should be to find the local min and the local max, right? So first, find all local min and max, again, on whatever interval we are given to look at. Yes? Then, step 2, find the coordinates. Find the coordinates of the endpoints. What are going to be the coordinates of the endpoints? There are clearly going to be x1, f of x1, and x2, f of x2, because we are talking about the interval x1, x2, and that will be given in the problem. We don't come up with that, it is given. Step 3, simple. Step 3, make a list. Make a list of all the points in steps 1 and 2. Make a list of all the points you've identified in steps 1 and 2. And in view of that list, decide which one has the largest y value, and that will be your global max. And which one has the smallest y value, and that will be your global min. That's going to be our 3-step strategy. Pretty simple actually. So much of the work is to take place right here in the local min and the local max. Why? Because that requires the use of the derivative. Remember how do we find local min and local max? What do? We find the derivative, we find the critical points. What's a critical point? A point where the derivative is either 0 or undefined. We put that into a table, and if the table tells us that the graph changes from down to up, we have a local min. If it changes from up to down, we have a local max. So that's the kind of work that has to be done in step 1. Step 2 is easy. You take the endpoints and you calculate the y value for each. Step 3 is easy. You make a list of what you found in the first 2 steps, and you make a decision in terms of which one is the highest, which one is the lowest. That's what we're going to do on the next example. All right, so out with this. All right, so example. Find the global minimum and maximum. Find the global minimum and maximum for the function f of x is equal to the cube root of x times x squared minus 7 on the interval 0 to 8. Find the global minimum and maximum for the function f of x is equal to the cube root of x times x squared minus 7 on the interval 0 to 8. All right, so step 1. I need the global minimum and maximum. Keywords, 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 global. So that means I need my 3-step method, the one that I just presented you with. Step 1, we need the local min and local max. So this is what we've seen in the previous chapter. We know how to do that. First we need to find f prime of x, right? The local min and the local max, they come from f prime. This is my f, so I need to derive cube root of x times x2 minus 7 prime. I wrote the cube root of x as x to the 1/3 simply because it is more convenient to do that. And now I have several ways of doing this. I can multiply this in, or I can treat this as a product rule. Let's practice our product rule, something we haven't seen in a short while. So product rule, the derivative of the first one times the second one not prime, and then reverse x to the 1/3 not prime times the second one prime. Good. All right. Good old exponent rule, rule number 4. We remember, very useful. 1/3 x to the 1/3 minus 1. What's 1/3 minus 1? If you answered minus 2/3, you are correct. Plus x to the 1/3. That's an easy derivative because the derivative of a minus is the prime to each. The prime of x squared is 2x and the prime of 7 is 0. So my non-simplified derivative looks like this. Why do I say non-simplified? Because basically x to the 1/3 times x to the 1. I say non-simplified because I need to take a common denominator before I can actually consider this expression fully simplified. So I did bring the minus 2/3 downstairs. The 3 was already down. I put the 2 in front. I could have multiplied x to the 1/3 and x to the 1. What would I have gotten if I had done this? I would have gotten x to the 1/3 plus 1, or x to the 4/3. So common denominator. This is x to the 1/3 times 2 times x all over 1. So the common denominator is clearly 3x to the 2/3. That's already over 3x to the 2/3. So all this is x squared minus 7 plus, what did we say that was? What's x to the 1/3 times x to the 1? We said this was x to the 1/3 plus 1, so x to the 4/3 times this guy, 3x to the 2/3. Lovely. Interesting derivative. So what do I have? X to the 2 minus 7 plus 6x to the what? That's 6 because 2 times 3. X to the 4/3 times x to the 2 over 3. Those rules of exponents we saw in the first review video way back in August, they're still super useful. X to the 4/3 times x to the 2/3, so I have to add my exponents. 4/3 plus 2/3 is 6/3, which is 2. And now, this is better, but it is not fully simplified. Pourquoi? I have like terms in the numerator. X squared plus 6x squared is 7x squared minus 7 over 3x to the 2/3. That looks good. Is it fully simplified? Nah, because I can take out a 7 and I'm going to get x squared minus 1 over 3x to the 2/3. Is that fully simplified? No. Because this is a difference of squares. So my derivative is 7 x minus 1 x plus 1 over 3 x to the 2/3. Wow. All right, that made us work. Not only in terms of derivatives, because after all, right here in my 1, 2, third line, I didn't have any more derivatives. So that was considered a DNS answer. But you see that in this section, we need to go DS. We need to fully simplify so that we can actually extract the critical numbers from this guy. Ha! Okay, so we're not done with step 1. We have the derivative. We need to find the local min and local max, which means we need to find the critical numbers of this guy. So step 1 continued. I'm just going to keep this guy over here so that I can actually have what I need. So step 1 continued. We need to find the critical numbers. Find the critical points or critical numbers for f prime of x. What are the critical numbers for f prime of x? Remember what critical numbers are? These are numbers that actually make f prime 0 or f prime undefined. Recall, change colors, recall, change colors, recall, critical numbers make f prime of x either 0 or undefined. And we know what this means, right? F prime 0, this means the numerator of the fraction is 0. F prime undefined, how do we get something that is undefined? When the bottom is 0, when the denominator is 0. So we got our work cut out for us here. We need to figure out where is the, let me rewrite f prime here the way we have it. 7 x minus 1 x plus 1 over 3 x to the 2/3. Did I copy this right? It looks good. I can erase this. So to find the critical numbers, I need to find the numerator equal to 0 and solve, and then denominator is equal to 0 and solve. So numerator equal to 0 will mean 7 x minus 1 x plus 1 equal to 0. Clearly, 7 should be 0 or x minus 1 should be 0 or x plus 1 should be 0. But the constant 7 is never 0. And as for these two, I get two critical numbers, 1 and minus 1. So I get two critical numbers from the numerator. What will I get, if anything, from the denominator? The denominator being made equal to 0 yields 3. X to the 2/3 is equal to 0. I can divide both sides by 3. What is 0 divided by 3? 0. So this is the same thing, just to fix the ideas. This is the same thing as the cube root of x squared is equal to 0, right? You want x, so the best way to get rid of a cube root is to cube both sides. The cube root cube will give us x squared, and 0 cube will give us 0. So that x is equal to plus or minus the root of 0, or simply 0. So at the end of this analysis of the numerator being 0 and the denominator being 0, we end up with 3, so conclusion of this part, 3 critical numbers. What are they? Minus 1, 0, and 1. Now, remember step 1 is about finding the local minimum and local maximum. These can only occur where the critical numbers are. So we have the critical numbers, but we don't know which one happens to be a local minimum and a local maximum, if any of these two. So we need a third whiteboard for step one. Let's get rid of this and let's figure out what is the outcome of step one. I'm going to keep that in the picture for 1 second because now I am going to need a table of variation to figure out who's who. And who's who will be told when I solve this table. So in here, I'm going to put my critical numbers, yes. And then here, I'm going to put f prime and f. Okay, what do I do now? Well, I'm going to need to recall what my derivative was. I'm going to put it down here over 3x to the 2/3, which I choose to write as the cube root of x squared for now. And basically, remember the strategy. Let's change colors. We need to pick numbers in each of these intervals and put them in here and decide on what sign is actually going to do that. So we'll do one together and the other ones I'll just put into the table because it's just calculation. Okay? So I don't know, between minus infinity and -1, let us put -2. So let's do it here, f prime of -2. So we're putting -2 into here, so 7 times -2 minus 1 times -2 plus 1 over 3 times the cube root of -2 squared. That's a plus, that's a minus, that's a minus. So that's a plus, that's a minus, that's a minus. What's the bottom? What's -2 squared? It's 4. Cube root of 4, I can do it on my calculator, but it's going to give me 1 point something, a positive number, times 3, which is a positive number. That's a plus. So a minus times, a plus times a minus divided by a plus should actually give me what? A plus. And we do this for the interval -1 to 0. What number would you pick here? -1/2, yeah. 1/2, 2. We put them in and we get this. You don't have to believe me, you can verify this for yourself, but I don't want this video to be too long or longer than it should, so I'm providing you with these symbols. They're just calculations, that's all they are. And now, if f prime is positive, do you remember what it means for f? What does it mean for f? It means that f is increasing and decreasing and decreasing and increasing. Aha! Now we got a clear picture of who's a local min and who's a local max. Check it out. At -1, the graph goes increasing and then it goes down. What do you call a point right here? That point is actually a local maximum. In here, down, down, nothing happens. And here, down and up. What do you call that point? That marker is finished. That point is actually a local minimum. So we have what we were searching for, local max right here. This is nothing, and this is a local min. So, step 1 complete. Step 1 is now complete. F has a local max at -1, comma, a y value that I will have to find. F has a local min at local min at 1 comma something that I'll have to find. Where do I actually go to find the f value? I go into my, well, it's an f value. What's a synonymous thing for f? Y, right? So I need the y value, the f value, so I need to go back to what f of x was. Cube root of x times x squared minus 7. So once again, these are just values. Cube root of minus 1 is minus 1. Minus 1 times minus 6 is 6. 1, 1, minus 6. You can verify those by yourself. So that is the outcome of step 1. All of that to get those 2 points. A lot of work in step 1. Let me see if I can finish this quickly. So let me get rid of this here. I don't really need that. I can go to step 2. Step 2. What was step 2? Step 2, find the y value of the interval. Did I give you the interval? The interval, I don't remember if I gave you the interval. The interval was 0 to 8. I think I did. So now I need to find f of 0. And I need to find f of 8. Once again, remember that f of x is the cube root of x times x squared minus 7. If you put 0 in there, you're going to get 0 times minus 7. And if you put 8 in there, you're going to get a big value. The cube root of 8 is 2. 8 squared is 64 minus 7 is 57. 57 times 2 is 114. So these are my endpoints. The end points are 0, 0 and 8, 114. That is the outcome of step 2. So this is what you get up there in step 1, and this is what you get up there in step 2. Good. So to complete the problem, we make a list, which I've already conveniently done over here, and I simply find the largest y value and the smallest one. Largest y value is what? Smallest y value is what? The largest of these y values, here are your choices. 6 minus 6, 0, 114. Clearly, the largest value is 114. And that means that 8, 114 is the absolute max. What is the smallest y value? Your choice has to be between 6 minus 6, 0, and 114. The smallest y value is minus 6, which means that 1, minus 6 is my absolute, also known as global, minimum. And voila. These are the answers that we were looking for in this long problem. All right, so we got enough done in one session. Don't want to go way above half an hour on this, it's enough. So that's the overview of global min, global max. If you already understand local min, local max, it's really just an extra small procedure that goes on top of what we already know. So that's it for today, and I wish you well. I'll see you for the next one. Take care.